Hey there, class. We're here to look at an example. This is example 9 from our Physics 1, or it's example 7 from Honors Physics. So basically what we have is a box. It's at rest, begins to slide down a frictionless inclined plane. Now this is a very large inclined plane. It's 125 meters long and 25 meters high. So this is very, very large. But this is an example problem that's connected to something else. Another example that I want to look at, and so we've made it maybe a little unrealistic to show a point that you're going to see later. But for all intents and purposes, let's get started with this problem. So basically what we have is we have this inclined plane, and this inclined plane, again, this object starts at the top, and it slides down frictionless until it gets to the very bottom. So initially it does have a height. That height was, of course, according to what we read, was 25 meters. And it ends up, I think for convenience of this problem, we'll say it ends up at the ground at the end. So what's going to happen here, looking at this from an energy perspective, we want to ask ourselves two questions. For potential energy, we always ask ourselves, is it raised above our zero level? In this case, the ground. And the answer to that, of course, is yes. So we can calculate by taking m times g times h, in this case, h original. The next question we want to ask ourselves, is it moving? And here in our original snapshot, we are told it's starting from rest. So basically, the kinetic energy is going to be 1/2 times mass times velocity original squared. In this case, this is 0. So therefore, the kinetic energy is also 0. So total energy-wise, the total energy we have at the beginning is simply due to the original potential energy. Now let's go down and look at what happens at the bottom of our ramp. Down here at the bottom of the ramp, the object has reached its lowest point. So mgh final, because the final height is going to be 0, that's going to actually tell us that potential energy at this location is 0. Here, 1/2 mv squared, and again, this is our final velocity, and certainly at this point, it's going to have some velocity. In fact, I think this is what we're trying to find in this problem. So this is a non-zero number, and so therefore the kinetic energy is going to be a non-zero as well. So total energy at the end is going to be due to just the kinetic energy. And so basically, as far as energy goes, if we take an energy standpoint, look at this. What we are assuming, because there's no frictional forces, since there's no frictional forces, all the total energy that we start with has to equal all the total energy at the end. And so that's part of our strategy and how we're going to implement to solve this problem. So the basic strategy here is that since there's only conservative forces, in other words, gravity is really the only thing doing work here, it's what pulls it down the ramp, that means we can use the conservation of energy. And the conservation of energy basically states that the total energy we start with has to equal the total energy we end with. Now, according to what we said in the picture, the total energy we start with is, it was potential energy because it was raised above the ground. So that was our original starting energy. And the energy we end with was the kinetic energy because there was no potential at that point in time. So that was our final energy. Now, potential energy is found by taking mgh, and kinetic energy is taken by 1/2 mv, in this case, it's the final velocity squared. And again, what I'm doing here, I want to solve for the VF. All right, so to solve for VF, I'm going to actually divide by 1/2 m. Okay, that will, all right, that's going to cross off these two things, and over on this side, 1/2 m. Okay, when I scroll down here, what's actually going to happen here, this m is actually going to cancel out that m. And when we do the algebra, since you're dividing by 1/2, it actually ends up being 2 times g times h original, and that's going to equal the vf squared. Okay, the next thing I'm going to have to do to get vf by itself is I'm going to have to square root both sides. When I square root a square on the right-hand side, I'm just going to end up with what's inside the square root. And over here, I'm going to end up with 2 times g times h original. All right, I'm at a place now where I can actually substitute in my values. So I'm going to substitute in 2 times 9.8 newtons per kilogram times a height of 25 meters. And that's going to equal the final velocity. So let's go ahead and get a calculator and see what we get. Plugging my values in and doing the math here, I end up with a speed of 22.14 meters per second. So to respond to the question, which was how fast is the object going to be moving at the end, I would say it's moving at 22.14 meters per second.